explained a lot. All right, so here we go. So on the next page, and the page after this, we're asked to find the force of the wall. What do we next? The previous force of the wall, I think we had to find.
Yeah.
All right. So Naomi, you did a good job finding all the forces. So I'm going to launch this tango board, and you're going to help me do all the forces or some of them. Give me a second. So
I'm drawing.
well, no, you can just tell me what to do. So what? Give me one force that's on the ladder. The first step in doing any torque for any physics problems. What are all the forces on the object? This is called a free body diagram. It's tremendously useful. It's almost always the first step. Before you proceed, you really want to get the free body diagram. So, Naomi, I'm going to wait a little bit. I'm going to pause. Okay, Naomi, what do we do here?
F wall.
I agree. I like that name, F wall, and that goes perpendicular. F wall. Go ahead. Give me another one. Give me one more in the bottom. We'll stop there.
Friction.
Friction that is really preventing the ladder from sliding. I think it's the only thing preventing the ladder from sliding. Tiffany, could you give me? I think it's just one more force, right, Tiffany? What is it? So now you have to get an angle here. So it's called the force of gravity, or if you like, mg, whatever you like. And I think is that all that you had to do on the first page? And you had to find the angle in there. Is that what it tells you to do? What was the angle, by the way? I'll clean it up. All right, so these are the forces: the friction that prevents the ladder from sliding, the weight of the. Oh, where do you place the weight, Tiffany? The weight of the ladder always in the. Yeah, we're gonna do all our objects will be uniform. We always place the center of mass, the weight in the middle. Good job. And what was the angle? Did you ask to measure? What was it? Yep. It's this guy right there at the bottom is 50, 50? Yeah. 50, okay.
It gave us the angle.
Oh, okay. 50 degrees. Now you mentioned before about the angles, and once there's an angle it's not 90, we have to use the sign. What other angle should we really find? Yeah, this guy here is 40 degrees. If you don't see what Miss Beninati sees, she sees a right triangle, right? See the right triangle. So if there's a 90 on the bottom, that 40 degrees is going to be critical when you do your torque problems. And the next page, I think you asked to find, what was, Francesca, what was the question? The sum of the
forces in the x and y direction.
Well, you know the answer to this. Sum of the force in the x direction equals how much?
0.
Of course, it's an equilibrium. The sum of the forces, in the y direction also equals 0. And is that all you had to do? The force of you had to find the force of the wall?
Yeah.
Well, we can use the x, right? The force. So using this, did you write anything? The force of the wall will simply equal what? Force of the wall has to equal the friction. Because the left equals the right, so I can get that. And what about the sum of the? Then we asked to do the sum of the force in the y direction too. Okay. How about Kayla? Would you do me a favor and get this? So the ups equal the downs. That the normal is an up. Any other ups in this picture? I don't think so. Right? Yeah. I think it's the only up. And the downs. There's just one down. What would that be? Right. Now in your lab, I actually ask you to. I'll be asking you hang a little weight over here, and so that will be the other down, won't it? So keep that in mind. Not in this example, but you're actually really smart to do the torque one first. I should have placed this question a little higher, but you're right. We could still do it. But you're totally right. I agree. You really should do the torque first. Good call, Eva. So now let's do the torques. Sum of the torques, Eva, equal.
Yeah.
Beautiful. And what did we say that a really good place to put a pivot? Yeah, I love that because it knocks out. Actually, I was going to say it knocks out. Really, it doesn't knock out two unknowns because why do we already know the normal force. Why is that? Why do we know the normal force? Because it's simply going to equal the Fg. So why don't we do that now? Just always put the picture. So what was the mass of our ladder? 15. So 15 times 9.8. Did somebody do that?
147.
Okay, so equals 147 newtons. That's that right? No, wait. Is that high?
Yeah, that's why.
147 newtons. Yeah, you're right. Okay. All right. Gotcha. So I could love to put the information in the picture. No, but it still knocks out one of the unknown, the friction. And so using that as a pivot. Okay. I'm going to need to clean up a little bit because I have no more room to write. Let's do the sum of the torques. Did they say how long this ladder was? Of course they had to, right? 5.0 meters. This is our pivot. Okay, sum of the torques equals 0. And how many torques are there? Well, there's a torque from the weight. Could you give me that again? 147 What?
47.
147 newtons. And there's another torque over here, which we don't know. We'll call it F wall. Or I'll be lazy and call it F. I think those are the only two torques, right?
Yeah.
And we found that since this was 50, you told me this, they told you it's 50, of course, that's 4. And so, all right, some of the torques, there really are two opposing torques, each one equal to, well, we usually do 9.8 in the lab. Okay, so the big torque, where's well, actually, it's not a big torque because both these torques have to be equal. So let's do the F wall. F wall. Now, what do we have to do now? What is that angle in there?
Sine of 50.
Yeah, that's 50 degrees as well. You got that Z that you learned in math. Two parallel lines cut by a transversal. Sine of 50 degrees multiplied by the moment arm. You told me it's 5 meters. And that equals the other torque, which is 147 newtons, sine of 40 degrees times the moment arm. Well, the moment arm's not 5 for this one. The moment arm is 2.5. And I don't know what it comes out to be. Maybe you can tell me what it comes out to. What did the F wall become? 62, is that right? 62 newtons? And then by knowing the wall force, we also get to know the what force equals the friction. Yeah, that's terrific. In your lab, the challenge in your lab, I'm going to give you a ladder. I'm going to give you put it against the wall. My challenge for you is, can you find the coefficient of friction? Did I ask you to do that in this page? I don't see. Is that the next?
You did.
Ah, so what equation will we use to find the coefficient of friction? Right. Right. Great. So I know the Fn, don't I? Because I knew it was equal to the weight force. I now know the friction. So would somebody help me out? What was the normal force? Was that 147 newtons? And what was the friction from before? Because from this, 62. And we divide both sides by 147. What did it end up being? 0.42. No units, right? Let's see. How about a little review? What is always true about a coefficient of friction? It's always what? Always true, all the time. Yeah. So if we're doing a problem, we get something greater than 1. We say, "Oop," and we got something. It doesn't necessarily mean we're right because we got less than 1, but we know we're not. It's probably right. There's a higher chance that it's right, and that's how you do over here. Now, remember what I told you on your lab. I'm going to ask you that there'll be hooks on your ladder, and I'll say place a weight on the top, and that means there'll be now 2 torques: a weight torque from the ladder and the hanging weight, and those 2 torques will be equal to the torque of the wall. Okay, so that's that. Yeah. Got a question? Let me stop this.